Chris, would you like to speak?
Yeah, hello again. Let me throw some, oh, I can't do screen sharing. Is there a way that you can activate that?
Yes.
I put together some slides.
Go for it. Should work.
Okay. Then let me start this presentation. Oops. Okay, can everyone see a PowerPoint slide?
Yep.
Yes.
Okay, excellent. So again, my name is Chris Madugo. I'm a geologist with Pacific Gas and Electric. And I just put together a few slides. I was going to, at a very high level, go over the fault mapping course, or what you'll learn. And then I wanted to give you a little context of how this is used in industry. So I'll tell you a little bit about Pacific Gas and Electric and our geosciences department. And then I'll run through a fault mapping example that I put together for the course last year that I thought was pretty effective. And then I'll end with some research needs that PG&E is specifically interested in, which is why I'm involved. So in this course, you're going to learn how to identify geomorphic indicators of active faulting, and then use that to develop active fault maps. And this is important because this is the starting point for any fault hazard mapping study done in research and industry. And then you're also going to learn some standard GIS practices for fault mapping. And when we ran the course last year, it was really good synergy between academics. There were several people from industry that were involved, and it provided context for what you're learning in this class. Let's see. So before I get into Pacific Gas and Electric, I guess I'll talk a little bit more about myself. My background is similar to Rich's. I've been working on this for 20 years or so. I got my did my undergrad at Occidental College, master's at Central Washington University. And when I started my master's in 1999, there were 3 big earthquakes: the Chi-Chi earthquake in Taiwan, earthquake in Turkey, and earthquake in Southern California. And these were all just great earthquakes to study for active tectonics. And I ended up studying the Landers rupture in Southern California, also went over to Taiwan and looked at that. And those earthquakes just got me hooked on doing active fault mapping and also paleoseismic trenching, better understanding the earthquake history of faults that have ruptured prehistorically. Large earthquakes happen so infrequently on the scale of a human lifetime that you have to find ways to look back into the past. And active tectonics, the study of active tectonics is one way to do that. So let's see, my master's then for PhD, I went to Oregon State University and studied active faults in the Indian Himalaya. A lot of those faults at the Himalayan front, there's lots of people living on the faults, and there's lots of hydroelectric systems and infrastructure on the faults. And one drumbeat in the background of my education is I wanted to use this maybe more than just for research, but to do something meaningful, apply it to the study of hazard for facilities, dams, electric systems, gas lines, et cetera. And I've worked in the consulting industry throughout my academic career, and then ultimately landed at Pacific Gas and Electric, which is a great place to apply my knowledge of active tectonics. PG&E is a utility that serves 16 million people in California. The service territory extends from Oregon all the way down to just north of LA. And we have a lot of different types of facilities within our service territory. So corporate real estate, that's something we can all imagine. That's just buildings that are scattered throughout the service territory. Hydropower, there's 170 dams within the PG&E system, and all those dams have tunnels or canals and powerhouses connected to them. They all have power lines that connect the dams to population centers in other parts of California. We've got one nuclear power plant. And then we have a lot of linear, or called distributed infrastructure, so electric and gas lines. So these fall into the transmission type that take gas or electricity from town to town. And then there's distribution that takes the gas or electricity to your house. And the distributed assets, you can't avoid faults. Like a building, you could relocate. You could find out where the fault is and relocate it. But the power lines and gas lines, they're going to cross faults. Like the gas lines are buried. And so you need to understand what the fault is where the fault is in reference to the line, what the fault could potentially do to the line, how it would deform it. And then if through modeling, you find out that that's an issue, then you do a mitigation. You make the gas line stronger, or you reorient it so it can better accommodate deformation. PG&E is very unique in the fact that it has a dedicated geosciences department that includes geologists and engineers, seismologists. And this is something that came out of the licensing agreement for our nuclear power plant. Our power plant's located on the central California coast. And there's lots of active faults in that area. And so when the plant was being licensed, the company made a commitment to staff a geosciences department that would keep tabs on the latest research and do its own research on the activities faults, maybe find new faults and see if there was an impact to the plant. And over time, that was in the 70s, over time, that department has expanded to do geosciences support work for the entire company. And my role is primarily to study faults, but we also look into landslides, erosion. We do storm response. So that photo at the bottom here is the 2016, 2017 El Nino storm season. There's a lot of damage to our system. One big part of an infrastructure system is roads to get to all of your facilities, and a lot of roads were washed out and damaged by that winter. So our group helped identify issues after those storms and help plan repairs. So my focus, as I said, is primarily on source characterization. I do that both for ground motion studies. So I develop catalogs of faults in California, help identify how large earthquakes could be on those faults, the rates that those faults are moving. And then I work with a team to develop ground motions for each of our facilities, and then mitigations if necessary. The other part of my work is mostly for gas transmission. And so this is a snapshot of the Bay Area with all the main faults. This is the San Andreas system, which includes the Hayward fault and other faults in the Bay Area. And then the little green lines are gas transmission lines. And so all the dots are where the gas lines cross faults. And since I started PG&E about 7 years ago, we have studied all these crossings in the Bay Area, and we've started doing mitigations where needed. Not all the crossings need mitigation. In some cases, the gas line will do just fine if there's an earthquake. In other places, as I said, you need to make the line a little bit stronger, or you need to change the orientation the line across the fault. So here's the mapping exercise that I put together in Google Earth. Just quickly, sorry if it's a little hard to see, but this is related to the 2019 Ridgecrest earthquake. So out in the desert, even though our service territory only goes down to Bakersfield, we do have some lines that extend to other parts of California, and our main transmission lines where we get our gas from go outside of the state. Some of our main lines come from Texas, and then I think all the way up in Canada are a couple other lines. But this is in the Ridgecrest area, and so this is an image just showing the desert, and in yellow is our gas line. It's part of our gas line that serves the town of Ridgecrest. And then in orange are faults that have been mapped by the USGS fault and fold database. These are mapped for use at a different scale than you're seeing in this image. The scale is at the lower left, and you can see the scale shows maybe close to a kilometer. But at this scale, the faults may not be directly on the geomorphic features that are related to those faults. So for PG&E, we use these maps as a starting point, and then we do more detailed studies. We have to map exactly where the faults are and how they're oriented at our infrastructure. So in this area, we would take this orange line as a starting point, and we'd look at imagery, LiDAR, whatever geologic maps. And we'd also probably do a field trip to go out and look at the site and do more detailed mapping. Here's a LiDAR image, and you can see there's this feature crossing right here, which is kind of parallel to the fault that's been mapped here. So the fault is probably in this area here. And let me back up. What you can see in this image is a bunch of different things. You can see drainage patterns. So you can kind of see this north or south to north drainage pattern here. Some old fan remnants or pediments. You can see these ridges here. It's a little mountain here. You can see this weird feature here, which is in the field with Mindy, and we actually found out that this is wind-blown hay from some burrow corrals, wild burrow corrals just off the screen. But when you're doing the geomorphic mapping, you're looking at all this and trying to put it into context and look for indicators of fault activity. So with the LiDAR, you can see this trend right here. And two researchers after the 2019 Ridgecrest earthquake sequence did some detailed geomorphic mapping to see if they could identify evidence for the faults that ruptured, before they happened. So they just used imagery and whatever they had available from before the rupture. And they identified this feature as where the fault was located. And here's some of their mapping. So all these lines are their geomorphic mapping of where the faults could be located. And they identified geomorphic features like this linear ridge right here. That's not where a fault would necessarily be, but that ridge may have been uplifted by active faulting. So it could be bounded on both sides by fault. And so this set of aligned ridges goes along in this direction. And so that may be where the main strand of the fault is located. They identified abnormally linear drainages. So you see this kind of meandering arroyo here, but this section right here is really straight. So maybe that's fault controlled. There's an aligned set of drainages here. There's a tonal lineament here. So this wasn't done by PG&E. We hadn't studied this site yet, but it shows you that had we looked at this site, this is the kind of map that we would have come up with. And then we'd be scratching our heads about the connections here because there's different fault crossing angles with our pipeline, and maybe some would be better than others. But this would be our starting geomorphic map, and then we turn it into a fault map that would have these features here that are indicative of faulting. And then we have some suspect features, like the linear drainages. These might be secondary faults, or may not be faults at all. The 2019 magnitude 6.4 rupture crossed our gas line. So this is a drone image by Rich and Ian. And so you can see the main rupture here crossing the gas line, and there's some secondary traces here as well. And going onto the ground, just looking down the road was built along the gas line for servicing the gas line. And so there was a left lateral displacement here. So it's a little hard to see, but the margin of this dirt road has been offset, 15 centimeters or so to the left. And so comparing this pre-rupture mapping, which we're doing in most cases for our infrastructure, because earthquakes are so rare, to the active fault rupture, here's how they compare. So I'll just go back and forth. So there's pretty good agreement in a lot of places. Where the fault rupture becomes more complex, the agreement isn't as good. Some of these secondary features, tonal lineaments, aligned drainages away from the ridge, were not related to faults that ruptured in the last earthquake. Maybe they are faults and they could rupture during a future earthquake. But the main rupture for 2019 followed these ridges, and then right in this area, right in our gas pipeline, it bent away. And so another thing that we do for our fault studies is we add an uncertainty zone. So we add a buffer around our fault mapping. And it used to be informed primarily based on judgment. Professionals that have done a lot of these studies and done trenching, and if you see this kind of geomorphic evidence for faulting, you can have a buffer zone of 50 meters, something like that. But more recently, we've been using empirical relations to inform those buffer widths. Zooming in here a little bit more about on the details of the rupture. So we've got the pre-rupture mapping in black, and then we've got the actual rupture in red. And what's really interesting to me is that this is the main rupture trace, and it's not on any of the mapped traces. So in some cases, it's good to have really large uncertainty buffers. And that's one research goal, to better understand how wide these buffers need to be. So research questions, more related to what you may be doing in academia. So what is the rupture location uncertainty for faults mapped with different levels of confidence? And we'll be discussing this quite a bit in this class. How does the uncertainty change with climate, geology, slip rate, et cetera? And what is the variability in rupture location from one earthquake to the next? Down at the bottom here is some information on the empirical relations that I was mentioning. This is Peterson et al. 2011, and there will be a lecture on this paper. But here, the researchers in developing a probabilistic fault displacement hazard model looked at the difference between pre-rupture mapping, which would be the straight line right here, and actual ruptures, like I just showed you, and then measured the difference between the two based on different confidence in mapping. Like a solid line is really confident, dashed line is approximately located, dotted is buried. And they came up with mean distances and standard deviation distances. So for an accurately located trace, mean was about 20 meters. One standard deviation was 26 meters. An inferred mean was 45 meters. One standard deviation was 72 meters. And some of the information that's generated in this class will be used to update these kind of empirical relations. So I don't know if there's time for any questions. Or Chelsea, if we're probably running behind time because I probably went over.
Yeah, there's one or two questions. We can have that, but then we should go on.
Questions for Chris? All good at UNR.
Thank you. Thank you, Chris. Yeah, so this pre-rupture mapping that Chris was showing is what we are going to focus on for the work of the semester. And then the later work afterwards is going to be to analyze the maps that you produce and see how close your maps were to the rupture, and then explore some of these different variables, such as climate, tectonics, and so forth. So let's move on. Just going to fairly quickly go over the syllabus, and then we'll hand it over to Rachel. We are meeting next week, Christy, even though the NorCal meeting is going on. So yeah, here's our course webpage. Put the link in, or maybe can't find it. Rachel, could you put the link in the chat, please? So this is our course page for spring 22. And the syllabus, which we'll talk about in a second, is online. And then every day, shortly after the class, we'll upload the lectures. Or that will be PowerPoints of lectures, and then we'll upload the class videos. So if you have to miss class, they'll be here. And then something you'll hopefully find useful soon is QGIS videos. And so this is videos that explain how to do far majority of the tasks that we will want you to do using QGIS. So please feel free to refer to these videos as needed. Are there any questions on here? Okay, so we'll go over the course syllabus just very quickly. A few of the main points. Hopefully you've all had time to read through it already. So we will be having frequent office hours. I think Rachel and I will have office hours on Monday next week, and we'll let you know exactly when. I think she and I will always have one office hour. One of us will have an office hour that you can connect to by Zoom. It'll be the same link as for the course webpage. And then public health rules accepting, then we'll also have one of us on campus for the office hour so that ASU folks can have face-to-face feedback. Later in the semester, when you're doing the main mapping projects, will require actually that you come into office hours every so often to get face-to-face feedback on your individual mapping. You are going to have frequent reading assignments. There's one due on tomorrow evening. And for each of these reading assignments, your homework is to do the reading and then write a summary of your assignment. And so you should write one paragraph summary of the reading, 4 questions that you have. And then for papers, what do you anticipate is the lasting impact of the paper? Why will people remember it? So you do that by 5 p.m. or so Mountain Time and send it to Rachel. You receive a small grade if you send it in on time. It's really easy. If you send it in, you get the full credit. Easy way to get full points. So send it in to Rachel, and we want it in the night before so that Rachel has time to review all of the assignments and then she'll generate some common questions for discussion the next day. Then we're going to have larger homework assignments, particularly for the first few weeks that will be weekly. These are to teach you how to do pre-rupture mapping. And those, again, really important that you turn them in on time, because we're going to review them, look at your shape files, and use them to generate discussion and feedback on your mapping. So please do not send anything in more than a few hours late. Better to be on time. It also then gets harder to grade assignments that were turned in after we've discussed them in class. To encourage you to submit things on time, if we don't hear anything from you, you will lose 10% of the possible grade each day it's late. And this really adds up quickly to not being good for your grade. So again, please turn assignments in on time. And if you really can't, get in touch with us and we can try to work something out. During the course, we're going to use QGIS and Google Earth. Rachel will discuss Google Earth in just a few minutes. So we don't expect that you've used any of these tools before. We'll teach you how to do everything that you need to know. We did ask that you have Google Earth downloaded for today and then QGIS for tomorrow or for Thursday. So if you have any difficulty installing these softwares, please get in touch. Many of your readings are going to be from this McAlpin Paleoseismology book. I did send out the PDF of this book, so you don't have to buy it. But it is a very good book, and so if you end up liking it, I do suggest at some point you buy it for a generally good reference. So yeah, then the second 2/3 of the whole course, we're going to be focusing on these main mapping projects. So that will begin in later February, so stay tuned. We'll give instructions for these later. Ultimately, you're going to be making high quality maps. We'll ask you to present your work in a presentation as well as a written report. And these will all be graded for your final grade in the course. So I'll stop there. Are there any questions?
Question from UNR, how do we find out our homework assignments?
So the first couple reading ones you should have seen in email, and then after that they'll be posted here. So the first mapping assignment we'll hand out on Thursday, and then it's already posted here if you want to get a preview before Thursday. And each one, these first ones at least, you'll have approximately a week to complete them, and the due date will be on the webpage.
Chelsea, there was a question about versions of QGIS. How recent should it be?
I'd suggest that you download the latest stable version. If you have a slightly older one, that's fine. But I don't think you want an ancient version. We're doing fairly standard operations, but I think the software did get more stable over time.
For those using a Mac, it can take quite a while to download the software. It took my system about 45 minutes or so to fully download it. So just be patient.
Yeah, so please do so at least by Thursday morning, early Thursday morning, so that it's ready to go for class. So on Thursday, Rachel will lead us through a tutorial on how to do common things using QGIS, such as do hill shades, make shape files for mapping, and so forth. Are there any questions?
All good here.
Rachel, are you ready?
Yes. So I'm going to talk a little bit about the project I'm going to be conducting throughout the course of this semester. And I might just share the screen for the project consent form just because it has a lot of the information on it already. But basically what I am setting out to do this semester is we want, at the end of the day, I kind of think of it as like a large funnel where the very top of the funnel is we have great pre-rupture maps that accurately anticipate where future ruptures will occur. And that'll help the goals of PG&E and just like basic geology, where can we put infrastructure, what are the hazards we can mitigate, how accurate can we make them. And so from last year to this year, we kind of developed a few exercises to try and study this mostly and see if the things we create are the efficacy of how accurate they can be. And so I have a consent form if you choose to participate in the study, and you can read this on your own time after the class, but it basically involves just 3 things throughout the course of the semester. The first one we're already going to be doing as an assignment, but if you opt in for the study, we will be using it to kind of analyze after the semester. And then the second one is going to be a short survey. It's a multiple choice kind of like scale to just assess your prior experience with the mapping. And I see that we have kind of a wide range of prior experience or knowledge in geology or active fault mapping, which will be quite nice. And then the third one is going to be probably what takes up the most amount of time, although it's not too much. It's a 30-minute recorded Zoom meeting where during one of the preliminary mapping exercises, we'll meet for 30 minutes and you'll just kind of walk me through your process of fault mapping. And the goal of this is to try and minimize the kind of inherent bias that mappers go through, whether it's conscious or unconscious. Like an example is if you're going up to an area and you already know it's kind of it's a strike slip fault on the San Andreas, you already have some kind of like preconceived notions of what you are wanting to see in the landscape that would reinforce the idea of where the fault is and what you want to see. However, with these exercises, we're trying to get students to come to these conclusions based strictly off of the observable evidence that you see in the landscape. And while it's kind of expected that as you become more experienced with mapping, some of this, not necessarily bias, but some of this is good because it can help you come to conclusions easier with knowledge. But we're trying to find a balance between getting the students to be skilled at this subject while minimizing the kind of inherent bias that comes along with it. And this will also kind of relate to the mapping confidence as well, whether, like Chris was mentioning, that you can use a kind of buffer zone or confidence based off of prior experience. We're hoping that with some of the modules and exercise we create, that it's going to be based more off of the evidence in the surface, that you can come to a conclusion of the fault confidence or your mapping confidence, and it'll be kind of more quantifiable than prior studies have done. And at the end of this, you can read it on your own as well. If you would like to partake in this study, you could sign it and send it to me hopefully by the next class meeting. And I did want to reiterate that it's not necessarily like if you guys are doing good or bad, it's more on us, like if what we are doing is good or bad, where you guys are kind of helping us test the efficacy of the materials. So I think it'll be really interesting if you would like to, and also no pressure at all. If you would not like to, you're more than welcome to opt out at any time during the study. If you do agree to it at one point, you're more than welcome to opt out at any time. But it'll be this guy, and then I'll probably lead into the simple and complex exercise. That'll be number 1 that you guys will be doing later as well, unless there's any questions right now.
There was a question from Veronica about having non-students being involved.
Yes, I think the way we worded it for the approval is just any kind of human study that will be using the same materials and exercises that we're going to be teaching. So as long as you can make the majority of the classes and get all the information we're hoping to give everyone in order to have it be kind of efficient and have everyone have the same materials, that'll be fine. Or as long as you can watch like the videos on your own time too, if you can't meet every time. And I think e-signature is okay.
Where will the consent form be posted?
Right now, it's on the course website under schedule. So I'll have, oh, there we go. It'll be right here. So the consent form right there. If you do
Okay.
choose to participate, the self-inquiry study, that's just like that initial study that we're trying to get a baseline for everyone's prior experience, will also be right there. And if we can get it before the next class meeting, that would be awesome.
And Rachel,
maybe-
we'll send it to you. Is that correct?
Yes, if you could email it to me, and probably also Ramon if you'd like to.
Yeah, Rachel's the point of contact. Just a couple of additional comments here. You know, this is a really good opportunity. And so one thing is for you guys as the students, you know, you want to sort of, you guys are pure actually in the sense that we think you don't actually know very much, which is a very good thing, in particular about the ruptures and this kind of work. And so the idea is, that's why it's really important kind of to have this, you know, do the self knowledge test and then do this complex and simple mapping exercise so that you can sort of see, you could track what happens to you in the class as far as you're learning. This is kind of a fairly standard sort of longitudinal kind of testing. And then just, we've done this kind of research before. I put a couple of other links in there. And so the idea would be that Rachel's going to write a paper about this. But, you know, to me, it's a fascinating problem, is how do we learn how to do this kind of work, any kind of work, but not use too much prior knowledge, because so often we see experts, you know, they say, well, I just know that's how it's supposed to be. I've seen a million faults. Well, that's fine. But how do we teach you guys? And you know, what we see is experts are usually right. They usually agree, but sometimes they're extremely different in their understanding. So why is that? And what we see with beginners is that they tend to actually have kind of wide uncertainty. So they're kind of all over the place. And so their uncertainty might span the actual knowledge, you know, but then over time, the expert, as you become more expert, your error diminishes and hopefully you end up in the right place. But to me, this is a fascinating problem, and it kind of digs into a little bit of the psychology of sort of how we learn about these problems and how we teach about it. So so you guys are, in that sense, the students or participants are subjects of the study. You know, this kind of institutional review board, this is a fairly common sort of thing at universities to make sure that people's, you know, rights are respected and that we don't take advantage of you. We think this is a relatively low stakes sort of activity, and we're not asking really, you know, difficult questions to you. We're assuming that this should be okay, but we want to acknowledge the formal nature of the human subjects activity.
The other thing is, if you choose not to participate, your grade will not be impacted. And if you do, your grade is also not impacted by the answers that you give during any of these activities. Elaine Young says, I'm working on a manuscript looking at overlap. That's a slightly different topic. Yeah, let's try to generally keep the chat related to really what we're talking about, like at the present, or maybe to quiet on the chat, because I think it can be a little bit distracting, especially for students and for me a little bit too. All right. Rachel, is it your Google Earth demo next?
Yes. So the exercise we'll be doing this week, it's kind of it also works to establish a base for you guys of how much you know about identifying faults from remote imagery. So on our course website, on the schedule, it'll be this simple complex mapping assignment. And then here we also have instructions too, if you need to refer back to anything I say when you guys are actually doing it. But when you click on this simple and complex mapping assignment, it's this KMZ file that can be opened up in Google Earth. Hopefully everyone's had some type of experience with Google Earth before, but it'll open up into this temporary places. And so the goal of this exercise is for the students to draw where they think the fault is within a defined area. It can be a very simple line as well, but we have two different locations. One is set to be more simple and easier to identify, and the other one is meant to be a bit more complex. And it's not meant to, like, if you got it right or wrong, it is just to kind of see improvement as well. So the first location, you can double click once you open it up into your Google Earth. We'll bring you down to our first location, and you will be identifying the fault within this general area. In order to do that, you can go up here to this add path button, and then per whatever nomenclature you want, just like your last name, first name, and then the location 1 fault. And you can make it red. That's kind of what we always do for the faults. And then wherever you think, I'm not going to do it inside it, but wherever you think the fault is, just kind of click it out. And then when you think you have it right, you can adjust them if you like. You can hit OK, it'll set it. And then that'll be that for the first location. This is meant to be the more simple one, and it kind of helps to identify faults when they might not be as explicit like they would be in a LiDAR or DEM. And then with the second location, we are going to be outside of Seattle. And then this one is displayed on a hillshade. It is meant to be more complex in the way that it's in a highly vegetated area, which tends to have more erosion, although this imagery pierces through the vegetation and tries to see the ground surface. And so the same thing with this one, you'll do last name, first name, location 2 fault, and then you'll kind of click out where you think it is. When you like where it is, you'll hit OK. And you can then save this to your places. You can save it as a KMZ, and then you can send it to me via email, and then that'll be it for that. This is probably going to be the only time you use Google Earth for fault mapping. It's just meant to be kind of an introductory exercise to kind of gauge whether or not you can kind of assess and locate within a certain amount of accuracy where the actual fault is located. From now on, we will be using QGIS, although last year I found it helpful to use historic imagery from Google Earth as well. So you can toggle back and still utilize this software, but you won't have to know too much about it from here on out just for this exercise. And then if you still have any questions about it, though, I have it all listed right here as well. It shouldn't take more than 30 minutes at most to do the whole exercise, and we'd like to have it turned in before our next class meeting on Thursday.
Can you remind us, Rachel, where to get the data sets from, and then how to open the hillshade in Google Earth?
Yes, I think the hillshade I've already embedded in the file when you download it, but if you go to our course schedule, it'll be listed right here under today's schedule. The simple complex mapping assignment will open the Google Earth KMZ file, and it'll go into your temporary places initially. You'll want to save it into your My Places after you've completed it, but it should already have this hillshade embedded in it. If it is giving you trouble, I will just upload the TIFF directly onto our course website, and then you'll be able to just kind of drag it in to your places and it'll upload correctly. But it should open up with the KMZ file. And then instructions are also right here. If you would like to submit the survey, you can kind of just send this with the survey and consent form all at once, or just the simple complex mapping assignment just before the next class. And again, if you're not participating, we won't use it as part of our study, but if you are, we'll just be kind of taking it more as an analysis after the course ends.
So the grade for turning this in before next class is counts the same amount as one of the homework reading assignments. And it's just that you turn it in. Again,
Yes.
not if you want to be included or the study, or if you want to be included or the study or not, that doesn't matter for the grade. It's just that you turn in initial mapping of this area before the next class. As Ramon says, don't look at other data, just do the exercise based on your experience. So don't look up what you think fault maps look like in this area. For example, Chris showed us earlier today that the USGS key faults are made at a different scale. So looking up that map will not help you for this exercise. And please don't refer to any other information. You do also have that fairly short reading assignment in the paleoseismology book that is also due before the next class. Are there any questions on anything we've covered today, or in particular what Rachel discussed and what your assignment is for the next 48 or so hours?
For the assignments, do you want us to just write it in the email, or do you want us to write it in like a Word doc and attach it to the email, Rachel?
Either is fine.
I would prefer like a Word doc or PDF just for file keeping for the course, but whatever you prefer. And if you do have any trouble with the simple complex assignment from now until Thursday, feel free to shoot me an email and I can help you troubleshoot.
I think we can't hear. I think that's UNR.
The question was, do you want us to label the email subject line in any particular way so that you know that it's from us?
Sure. I mean, if it's a simple complex, you can just put the fault mapping class and whatever it is that you're sending to me.
Fault mapping class and whatever you're sending.
And I will put the this video of the course on YouTube, probably be uploaded in about an hour or so. So if you want, you can refer to that. Or if you have questions, also you can email Rachel. Are there any questions?
Sounds good.
I don't want to like take time, but I do have a basic question as a non-tectonics person. So I don't know if that would be better after class or now.
Go for it.
It's in reference to how we define active faults. So the New Zealand Planning Guide doc that you sent defines it as less than 120,000 years, whereas the paleoseismology textbook defines it as less than 10,000 years. But as a planetary geologist, we're just identifying fault signatures on the surface and can't really define active. There's not like a geomorphic indicator really besides change detection that tells you active or not, right? Or is that like the secret we're going to learn this semester?
That is an excellent question. Maybe Chris has the PG&E perspective. For the purposes of the mapping, we are looking at faults that you can see as recorded in the landscape. And the time that they represent does vary also, as we'll see, based on the activity of the landscape. But as you were saying, different hazard guidelines do refer to active over different timescales.
Yeah, activity is a regulatory definition, and it really depends on what you're doing it for. In industry, it differs for houses versus dams. They all use different definitions of activity. But as Chelsea said, we're looking for impact in the landscape, and a lot of the mapping assignments that you're going to be getting have bedrock, but they also have alluvium, and you're just looking at how the faults are impacting those different units. With probably more of a focus on the Lake Quaternary units.
But on Mars, there might be
yeah.
different preservation or something like that. So,
Yeah.
something that just cuts the surface is probably maybe Mars active. So
Yeah.
But
Right.
we'll talk about that a little bit more later.
Okay. Thank you.
Are there any other questions?
Nada.
Active, yes, somewhat younger than what it cuts, but we'll see. Still some complications where you may not appreciate all faults with that exact definition. All right, great. So we'll see everyone on Thursday, and send the reading and the initial mapping assignment to Rachel. And then please have QGIS ready, downloaded and installed on your computer. And then we'll spend Thursday focusing on teaching you how to use the software. So,
Thanks,
have
Chelsea. Thanks,
Thank
everybody.
you.
Bye.
Thank you.
Bye.
Thanks.
Rachel,
Yes.
as far as the study that you're doing, since I'm auditing the class, I can't like commit to doing all the exercises. So do you want to exclude me so that you don't have a